I know what you're thinking. What does Mr. Stefan do when he's, just sitting around at home on the couch? I decided to make a video about sampling distributions and getting to one of the key ideas that's going to propel us into the rest of the school year. So what I have here is, imagine I have this population of data. And if I have this whole population of data, there are certain characteristics about a population that I can take and measure, like an average. Now, if I'm talking about a population of things that I'm measuring and find an average, I'm going to use the Greek letter mu. Not uncommon. We've used this already in the past. It means it's the population average. And then from that, I can also find the population standard deviation. Those are two things that I could measure. There is more. I could measure the variance, which is sigma squared. But now, what if what I'm talking about is a population of like Reese's Pieces, and I want to know the proportion of orange Reese's Pieces in a bag? Well, not in a bag, but like in the entire population. The entire population value for the proportion of Reese's Pieces is the lowercase letter p. Now, don't get this confused with the capital P when we're doing notation for like probability of something happening. That's a capital P, and that's a function. This is a lowercase p. All right, and then there's also standard deviation for the proportion of p. That would be the standard deviation of p. We'll get to how do you find that in a little bit. So then, now let's suppose that we're talking about over here in the green again with the mean and the standard deviation, and I have all these data points that I take a selection of, and I make a sample, and down here then I have this small subset sample. Each of those data points comes down here. Each of these data points comes into here. I do all of that. All those data points come into this little sample that I collected. All right. And inside of here then I have all those values, and let's say I collected n number of them. N can be 5, 10, 20, whatever. All right. But as I'm doing that, I have this sample of size n. And then I have the average, which will be x bar. And if I take all of these data points and plug it in through the standard deviation formula for a sample, I will get a standard deviation of s, or s sub, sometimes we'll say s sub x, of all those x values. All right. So what I'm doing is instead of mu for a population, I have x bar for a sample. These numbers up here, mu and sigma, are what are called parameters. That is some value that I get based on a population. The same thing is true over here. These numbers, since they're based off of a population, are also called parameters. Now remember, my red and my green are two different things, like two different pretend populations I'm drawing from. All right. So, and then these two values here are called statistics. A statistic is taken from a sample, and it's, in this case, a calculation. Now, if I were to take a sample of Reese's Pieces and count how many oranges there are, I will get a value based on a sample, and I call that p hat. So p hat approximates what the actual p really is, just like over here, x bar approximates what I think the actual mu is, and s approximates what the actual population standard deviation is. All right. Because again, in most cases, you're never going to be able to sample everything in a population. That is, you can't take a census. A census is if you take everything in the population. All right, so you have to take a sample, and then we make estimates about it. If I take all of these data points that I had here, that I get from my population, and I make a graph of them, and let's say I plot them on a dot plot, and whatever the variable is. Okay, I got these dots on here, and they all look like whatever the... So this is called a sample distribution. Or, in other words, it's the distribution of the sample that I just took. If I did a really well-constructed, simple random sample, this graph should look like the population data. Because if I have a bunch of data points on the left side of my graph in a population, I'll probably get more out of it when I take a sample. Again, this is assuming I do proper technique. And this is called a sample distribution. If I took all of the data points from the whole population and plotted it, I would get the population distribution. Let's say it looked like that. Now, there's, hundreds of thousands of data points. What we see is that my population and my sample distribution are actually pretty close to each other. But what we're going to talk about now is what happens if I take this number. So let's say I take a sample of size n, find the average and plot that, and do that repeatedly. Instead of me doing it like this, I'm going to go to here. So I'm going to start with this skewed right distribution. Let's make that a little bit bigger. All right. So I've got this skewed right distribution right here. This skewed right distribution is my parent population. It's the population values. All right. And what I'm going to do is I'm going to sample 10 items from that, and I'm going to find the mean. And I'm going to animate doing that. So there it collects 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. There's the 10 data points, and that found the average and it plotted it right there. And notice that these are all scaled the exact same. And then I'm going to do it again. There it is. It finds the average, plops it down. This is the population distribution. This is the sample distribution, and this is what's called a sampling distribution. All the words are very similar, so be very careful. And I will be very careful as I talk about it too. Population distribution, sample distribution, or distribution of the sample, and sampling distribution. A sampling distribution is a distribution of all values taken from a sample. So multiple samples. All right, so in this case, it's averages, or the mean. I'm taking the sampled mean of samples of size 10. And then instead of animating, I'm going to do 5 more. And then what it did is it did all those and then plotted the averages. And then do 5 more and 5 more. And it's going to continue to build. Now notice the x-axis stays the same. They're all 32. But the y-axis changes because I have more and more. And what ends up happening is, like when I do 10,000, I start to notice a relationship or some similarities and some differences. My original parent distribution is definitely right skewed. It had a mean of 8.08. That was given up here. All right. It had a standard deviation of 6.22. Ooh, can't get that to highlight. There we go. 6.22. And down here now I have a new distribution. It's a sampling distribution. Every data point in this distribution comes from a sample of size 10. And every data point in here is an X bar value. And if I take all of those X bars and I average all of those X bars, I'm currently have an average of 8.07, which is actually really close to 8.08. So I'm going to just give you a quick little, let's clear all this out. If I have a sampling distribution, X bar, and it's plotted, and that one actually looked pretty normal. Okay, so bear with me, that's not quite a perfect normal curve. It looks somewhat normal, but what I have here is all of these data points. And this one data point right there is the average of a sample based on 10 data points, because I did n equals 10. If I take the average, the population average of every possible sample, so if I would do every sample of size 10, and plot the X bar for every one of them, like say that's hundreds of thousands of them, what I actually will find is that it is equal to the average of the original distribution. So the two I had in that example was 8.07 was my current average of all those samples, and that's about equal to the population, which is 8.08. Now if I go back and do another 10, let's do 100,000, it did 100,000, so now I have 110,027 samples. My average of all of those right now is 8.08. The average of the original distribution was also 8.08. So you can see that it's basically there. But I had to get 100,000 samples to get there. It takes a while. The other relationship I want you to note is that the standard deviation of X bars, if you remember, look back at that graph, you can see that it's actually much narrower. The distribution of X bars is much narrower. It's actually narrower in a very specific way. If I take the original standard deviation and divide by the sample size, the square root of the sample size, I will get the standard deviation of the sampling distribution. All right. This is an amazing relationship that we're going to dive and do much more with. But before we do that, I want to say, well, what if it's, like I said in the beginning, not talking about X bars, but I'm talking about P or proportions. So here I have a Reese's Pieces machine, and if I know that 70% of them are orange, and I'm going to sample 25 candies, let's do that once and animate it, draw sample. So it draws my sample, and I found that my P hat, right here, the P hat from that one sample is 68%. That meant like 17 out of 25. 17 out of those 25 were orange. And then I'm going to plot that 0.68 down here. This distribution down here is a sampling distribution because it's all of the P hats that I'm going to do. I'm going to draw another sample. Ooh, 0.84, much larger. Draw another sample. Draw another sample. Draw another sample. And I'm going to have to animate a whole bunch. Let's do 20. And let's just draw those samples and do another 20 and another 20. And now maybe let's do 200. Let's see. Well, let me do 200. Yes, it did. Ooh, look at this. So every one of those little dots represents one set of 25 taken from the candy machine. All right. And we notice that the very smallest one's 0.4. All right. 40, we're 0.44. And then, you can see the last one I did was 0.44. And the highest one is 0.96. So while they're not all equal to 0.7, they're going to be centered at about 0.7. Right. There's 0.72. All right. And the further you get away, the less likely it is that those things happen. All right. If we're doing proper sampling methodology and we're doing simple random samples and we're going that route, we're going to be looking at how then, like, what happens if I get, what's the likelihood of actually getting 44%? If I do a sample and I get, oh, it's only 44% when it's supposed to be 70%, how often will this happen on average over time? Is that a really common thing? And we're going to find the answer is it's not actually quite uncommon. All right. Let me go back. Spotify. I want this. All right. If I'm doing sample proportions, so I'll go back to blue because that's what the color I was using for sample proportions. If I do all possible samples and find all of those sample P hats, the average of all of them will equal the original parameter P, that is the population parameter. And the standard deviation of all P hats will equal the standard deviation of all P's. But what this is going to be PQ over N square rooted. Okay? So P is the probability of success, that's this P here, times Q, which is, remember, from the binomial, 1 minus P. And then N is my sample size, and in this case, that would have been 25. And that's the relationship that I'll have, and that will be the standard deviation of my sampling proportion, of my sampling distribution of proportions. It gets to be a lot of language, so just bear with me as we go along. All right, and one more idea I want to get at here is the idea of an unbiased estimator. Unbiased means like there's no favoritism going into place. That is, if I were to do repeated samples and plotted my statistic for each time, the center of my sampling distribution will be about the same as the center of my actual distribution. And we did this already once, so we saw this was my original distribution. So here I have, I'm going to take the mean of samples of size 5. I'm going to take the range of a sample size 5. Let's animate the first one. So you see 1, 2, 3, 4, 5. And it plots, did that a couple times. Oh, I see, it did 2 different samples. The first sample gave me an average and it plotted it, and then it did another sample and found the range. All right. And if I do this repeatedly, all right, the center of my sampling distribution for means is going to be centered at, in this case, 7.22, about equal to the 8 point, but let's do 10,000. Let's just skip to the good. All right. Here, the average of the means is 8.10, which is awfully close to the average of my entire population. So the average down here, the average range is 14. And if I look up what is the range of this data set, I go from 0 up to about 30. Well, wait a second. If the actual range is 0 to 30, then that's 30. Is the average of all my ranges equal to the actual range of the population? It's not. It's actually much less. The average of the means, in this case here in the blue one, is very close to the original, so it's called an unbiased estimator. The average of all my ranges is actually quite far away from the actual range, so it's what's called a biased estimator. That is, there's some reason why it's not getting close. And the reason why is when you're doing any particular sample, it's unlikely you're going to get one from the very top end and one from the very bottom end when you're doing a sample, so your range is going to be much less. So if I'm going to do a sample and I get a range, my range value is actually not a good estimate of the range of the entire population. So blue here is an unbiased estimator. The green is what's called a biased estimator. All right, so now what I have going on here is I have on this left-hand side here, I have consider the blue target to be the actual population. And then my green is this sample. So I did a sample, and I have all these data points that are in the upper right-hand spot here, so it's right there. Are those data points close together? Yes, they are, so it's said to have low variability. And that makes sense. If it's not very variable, it's very close to each other, has low variability. And then we say, okay, did those points come really close to the actual value? Now again, I said the blue is the population. So my target, what I'm aiming for is this. Was I really close at hitting that mark? The answer is no, I did not. So it's called low variability, but high bias. All right, because it's definitely not unbiased. If it's unbiased, then it's what's said to have a low bias. So this is high bias, low variability. Down here in the bottom left, I have a whole bunch of points right in the bullseye. Are they close to each other? Yes, so it's low variability. Are they very close to what they're supposed to be hitting? Yes, so it's said to be unbiased or low bias. If it's an unbiased estimator, that means it's a good estimator. It has low bias. Over here in the upper right-hand corner, I have data points that are spread out. So that's called high bias. And they're not on mark. So it's also called, high variability. I did them both at the same time. Sorry about that. High variability because it's very spread out. High bias because it's definitely away from what the target was, because the target was the middle green. All right, so that being said, in your reflection response, tell me what this one is and explain why it is what it is. All right, there's only one choice left, but explain what about it makes it each of those two elements in terms of its variability and in terms of its bias. That's what you have to do for reflection response. There's a lot going into this video, so hopefully you're taking really good notes. Always taking notes. You have a much higher likelihood of remembering when you write things down. And also, now's the time when we should start reviewing for the end of the year. So anytime that you have a little extra time in the evening, be pulling out flashcards, anything from the first several chapters, refreshing your memory on terminology, but constantly reviewing at this point moving forward. That is if you're looking at taking the AP exam and being successful. That's all, folks, from my living room to yours.